In today's video, we're going to look at reactions as far as energy is concerned. We're going to look at a little bit about reaction rates, and we're going to look at how enthalpy is involved. And enthalpy is just a fancy word for heat, but how enthalpy is involved in these chemical reactions. Now, reaction rate is how fast a chemical reaction occurs. In AP, we get a lot deeper into this concept of the rate of a chemical reaction, but right now we really want to just look at why reactions occur in the first place, what's the theory behind that, and some factors that affect that rate of a chemical reaction. So in order for a chemical reaction to occur, these are the tenets of the collision theory, which is the theory behind why reactions do occur. The reacting particles must collide. And the more collisions you have, the faster the reaction occurs. So anything that will cause more collisions will result in a faster reaction rate. Now, not only do they have to collide, but they can't collide with just a wimpy amount of energy. They have to collide with enough energy to actually cause bonds to break and bonds to form. I always use a match with a matchbox and trying to light a match as an example of this. I can wave a match in the air all day long, but if I don't connect it with a matchbox, it's not going to react. And I can just kind of lightly strike it across the matchbook or the matchbox, and it's not going to light either because it has to collide with enough energy. It has to be struck hard enough in order to cause that reaction to occur. In addition, I have to collide particles in the correct orientation. And as an example of this, I simply turn the match around and try to strike the match on the wrong end. Well, if we do that, of course, the match is never going to light from that direction, so I must collide with the correct orientation. So they must collide with enough energy, and they must collide in the correct orientation. So if that happens, what are some things that can increase the rate of that chemical reaction? First of all, temperature. In general, the higher the temperature, the faster the motion of the particles, so you're going to get more collisions, so the rate's going to be faster. So that's one factor. Concentration. If you have a higher concentration of reactants, that means you've got more particles to collide. And the more particles that collide, the more collisions and the faster the rate again. Particle size. Now, you have to be careful because on tests, you have to notice whether they're talking about particle size or surface area. Keep in mind that if you have a small particle size, you grind a piece of coal up into dust. That small particle size means you have a large surface area, large amount of space where oxygen, for instance, can reach the coal. And therefore, if you strike a match, you hold it to a piece of coal, it's going to take forever to light. But if you strike a match in a container that has ground up coal dust in it with some oxygen, and you can get an actual explosion. So the smaller the particle size, the greater the surface area, and the more room or places for collisions to occur. A catalyst is a substance that increases the rate of a chemical reaction because what it does is lower the activation energy. And we're going to talk about activation energy in just a little bit. But for now, just realize that they do speed up a chemical reaction. They aren't changed in the reaction. They just speed up part of the steps for that reaction. So we'll talk about it again in just a moment. All chemical reactions involve energy in the form of heat. And again, a fancy term for heat energy is enthalpy, and a term you've got to be very familiar with. Enthalpy is the heat involved in a chemical reaction. Two things that can happen. The heat that is involved could be part of an endothermic reaction, and just like endoskeleton, which you've probably dealt with in biology, inside in, we've got an endothermic reaction in heat, taking in heat, absorbing heat. Heat energy is absorbed in an endothermic reaction. So if you absorb energy, that means your products are going to be higher in heat content than your reactants. Now, the container itself is going to feel colder because where did those reactants and that reaction system get its heat from? It absorbed it from the container and the surroundings. So it's just like sucking the heat out of it, so that container is going to feel cold. An exothermic reaction, heat exits, exit heat. Heat energy is given off. So what's the container going to feel like if a reaction system inside it is giving off heat? It's going to be hotter. Our products are lower in heat energy because they've given that heat off to the container, to the surroundings. So now, how does this look in graphical form? Well, here's an endothermic reaction and how we would represent it. And this is what it's going to look like, what you're going to have to analyze on the worksheet that you're doing for today. If you'll notice in an endothermic reaction, the general shape is always the same. We start down here with our reactants, and we add energy, add energy, add energy until we finally get the reaction started, and then we form our products. This original from zero, if we call this zero, whatever that distance is there, that's the potential energy of the reactants at that point. Over here, the distance from zero up to where the products end up is the potential energy of the products. This distance right here is the potential energy of the activated complex. Now, what is an activated complex? It is something that is formed in the middle of the reaction that is very stable and it does not last for long, but it must be formed in order for that change between the reactants and products to happen. And that's what usually takes all the energy. So that's why we always have a certain amount of energy that's needed just to start a reaction. For an endothermic reaction, we have to keep adding energy to it in order for it to keep reacting. So this distance, this energy right here, the distance from the reactants to this hump right here, that's called the activation energy. Activation energy, that distance. When we add a catalyst to a system, what the catalyst does is lower that activation energy hump. So if we had a catalyst in here and added it to the system, what would happen is we would have less activation energy needed. Therefore, we would have a lower activation energy. The potential energy of our activated complex would be lower, and our reaction would occur faster. So that's what happens when we add a catalyst. It lowers that activation energy hump. That's what it's often called. So how much energy is involved? The amount of energy involved is always the distance from where the products start, from where the reactants start to where the products end up. That distance is called delta H, or the heat of reaction. Since, and sometimes it's abbreviated delta H sub Rxn, the heat of reaction. And that change for an endothermic reaction is always positive. That's important. So if we had values here of 0, 10, this is, let's say that's 40, this is 30, this is 20. Okay, so those are some values that we have here. If those were the values, maybe you could see that the potential energy of the reactants is 10. From here to here is 10. The potential energy of our activated complex is 40, and it's saying it's measured in kilojoules. These are just pretend values, but let's say it's 40 all the way from here to the top. And let's see what our heat of reaction would be. Our activation energy would be going from 10 to 40. That would be 30 kilojoules if we wanted to look at our activation energy. Our heat of reaction over here would be going from 10 to, looks like about 30. So that would be a positive 20 kilojoules. So if we put numbers to that, you can see what those values would be. Now let's look at our exothermic reaction. Look at the difference in an exothermic reaction. In our exothermic reaction, we still have the same situation where we have the potential energy of our reactants, and over here, the potential energy of our products. So there's those same values hold. We've got the potential energy of our activated complex again. But let's look at how some of these values differ in an exothermic reaction. Look what happens. We've got reactants that start way up here. We need a little bit of activation energy just to get it started, and we end up with our products giving off heat energy. They're ending up at a lower energy state. So our activation energy here is quite small. Let's say that we started out at 0 down here on this reaction, and maybe this was 10, 20, 30. Not really doing a very good job of, let's make that a little taller. It's not to scale. I'm not going to worry about it. 30 here, 40 up here. So it looks like our potential energy of our reactants is about 30 kilojoules. Looks like our activation energy is only going from 30 to 40. So our activation energy is going to be quite small, only about 10 kilojoules. Our potential energy of our products, maybe somewhere around 20. Again, it's not to scale, but let's say that this goes from 20 up to 30. Okay, again, definitely not to scale, but 20 up to 30. So let's say this was 10 kilojoules. You've got to be careful because it's not a positive 10 kilojoules. It just lost from 30 where it started down to ish 20 where it ended up. So we're ending up here with a negative 10 kilojoules for our heat of reaction. We gave off heat. We have a smaller activation energy, so exothermic reactions often occur faster because they are giving off energy. They don't need much to get started, and they continually give off energy. So those are just some values that and some terminology that you need to know. Some of the definitions of the terms that we've been talking about are here later in your notes, so you need to take note of that. Use those when you have definitions. Gives an activation energy, activated complex, enthalpy of reaction or heat of reaction. All of those are given to you here, so be sure and notice where this information can be found.